If you've ever had to multiply two giant, messy numbers together by hand, you know it feels like a crushing weight. It takes forever, and one tiny mistake ruins the whole thing. Hundreds of years before calculators existed, people used a clever workaround. They found a way to translate these massive, heavy problems into tiny, manageable numbers that are much easier to move around. This translator asks one specific question: how many tens do I need to multiply together to make this number? If you feed it 100, it spits out a 2, because 10 times 10 is 100. When we use these translated numbers, the rules of the game change. To multiply 10 by 3 back into its original form, 1000. This same logic works for division too. Instead of struggling through long division, you just subtract the translated numbers and convert the answer back. This trick, called a logarithm, allowed people to bypass the most frustrating parts of arithmetic by turning them into grade school addition and subtraction. Of course, most numbers aren't perfect multiples of 10. If you give the translator an uneven number like 389.4, the answer comes out in two distinct pieces. The first piece is the size number. Since 300 is between 100 and 1000, its size factor is 2. This tells the translator roughly how big the number is. The second piece is the digit sequence. These decimal crumbs represent the specific order of the digits: 3, 8, 9, and 4. Watch what happens if we slide the decimal point to make the number smaller. As 389.4 becomes 38.94, and then 3.894, the size number shrinks from 2 to 1 to 0. But because the digits haven't changed, the decimal crumbs stay exactly the same. Because those decimal crumbs remained so predictable, mathematicians could print massive reference books filled with them. You simply looked up your sequence of digits and then added the size number based on where the decimal point sat. This system even works for numbers much smaller than 1. Since the size number tracks how many tens are multiplied together, a tiny decimal gets a negative size number. To keep the math tidy, mathematicians wrote these with a special bar over the top. This signaled that only the size number was negative, while the decimal crumbs stayed positive, so they could still be found in those reference books. The translator can also shrink exponents and roots. Since a square root is like repeated division, the translator handles it by simply dividing the translated number by 2. This creates a problem when you have a negative size number. You can't divide a -3 by 2 without getting a messy decimal that ruins your positive digit sequence. To fix this, people would artificially add a number like 20 to the total. This turns the -3 into a positive 17. Now the whole thing can be sliced in half cleanly, keeping the digit sequence perfectly intact. These barred numbers and addition tricks were simply the bookkeeping methods of the time, designed to keep a page of calculations organized and clear. Even when the translator turns division into subtraction, doing it by hand is still tedious. One small slip-up in a long subtraction problem can throw off the entire result. This progress bar shows a final shortcut called the complement. It's just a measure of the empty space needed to reach the number 10. Instead of subtracting a difficult number, you can just add its complement. Since you use 10 to find that complement, you just drop the extra 10 at the very end to arrive at the correct answer. This turns every remaining step of the calculation into simple addition, removing the last place where human error usually creeps in. By learning these translation rules, you gain a system that makes the most difficult parts of math much lighter to carry. Every operation becomes one step simpler. Multiplication becomes addition. Division becomes subtraction. Exponents become multiplication, and complex roots become simple division. Terms like size number or complement are just the labels on the controls of this historical machine. They were designed to keep everything organized while you worked. Logarithms were created to make massive, unmovable problems feel small and manageable. They remind us that even the heaviest math can be lightened if you have the right tool to translate it.